Good afternoon. We are starting Unit 3 today, which is all about functions. The first section is called Relations and Functions. So we're going to go ahead and jump right into some new material. A relation is a set of ordered pairs and can be represented in many ways. The first way, as you can see here, is called an arrow diagram. It takes the domain and draws arrows over to the range. It maps things onto them. So -3 maps onto 0, -2 maps onto 2, -1 maps onto 6, and so on and so forth. Ordered pairs are made up of two elements. The set of all numbers used as the first elements in the ordered pair is called the domain. So the domain is the set of first elements. And in parentheses there, I want you to put the x values, or inputs. And we'll come back to that a little later in the chapter. The range, on the other hand, is the set of second values, or second elements. And in parentheses there, I want you to put the y values, or outputs. And again, that'll become a little more clear later in the chapter. So, a discrete relation is a relation with a finite set of points. A continuous relation, on the other hand, is a relation with an infinite set of points So a finite relation is going to look like single points on a graph, while a continuous relation is going to look like a line, a curve, or any other shape on a graph. Now, some relations can be defined as what we call functions. A function is a relation where every element in the domain correlates to exactly one element in the range. So that means that for every x value, there's only one y value. You can't have any x value repeated with more than one element in the range. So looking down at the bottom here, we want to determine if each relation here is a function, and then we want to state the domain and range. So, example 1 has the points 0, 0, 1, 1, 1, -1, 4, 2, and 4, -2. And you should be able to notice pretty quickly. Well, 0, 0 is okay. It doesn't repeat anything. 1, 1 is the second point, but that 1 repeats. And it has different values attached to it. The same thing happens over here with 4 and 4, and it repeats and has 2 and -2. So this is not a function. Exclamation point because we're excited. It's not a function. If we want to list all the elements of the domain, we're going to say domain equals. And now we want to list all of the points. We want to use this fancy notation. We want to do a set of brackets, and we want to say 0, comma, 1, comma, 4. Those are all of the elements in the domain. If we want to list the range, we're going to do the same thing. Write range. Use those fancy brackets again. They take years of practice to master. And then you want to list out all the y values. So we have 0, 1, -1, 2, and -2. The one last thing you have to do with that is put them in correct numerical order. So to finish this, it needs to be -2, -1, 0, 1, and 2 with those fancy brackets around it. Okay? So this is not our final answer. You need to have them in correct numerical order. Example 2. Looking at this. You want to determine, does every value here match up with exactly one value here? Well, 5 goes to 3. That one's good. 6 goes to -8. That one's good. And -2 goes to +1. That is good as well. So this one is a function. And then we want to list the domain and range. So the domain, I'm going to abbreviate so I don't run out of room, is going to be in order -2, 5, and 6. And the range in order is going to be -8, 1, and 3. I know I ran out of room there. I apologize. I can write it a little lower. -8, 1, and 3. So you can see it. Example number 3. Well, we need to determine, is this a function? 2 goes to -6, so we're good. 4 goes to 14, we're good. -8 goes to -4 and to 14. So no, this is not a function. We want to list the domain. So going from least to greatest, the numbers in the domain over here are going to be -8, 2, and 4. The elements in the range are on the other side. They're over here, and we need to list them in order. And we have -6, -4, 12, and 14. Sorry, I ran out of room there again. We'll have -6, -4, 12, and 14 with those fancy brackets around them once again. Super. When a relation is graphed, we can determine whether it's a function by using what we call the vertical line test. So the vertical line test says that something is a function. So it says, we'll be more specific, a relation is a function if there is no line that can be drawn that hits the function more than once. So, looking down here, the vertical line test. If no vertical line intersects a graph in more than one point, then the graph is a function. So if you take and draw lines all up and down through this, you'll notice that these red lines don't hit more than one time. So this would be considered a function. On the other hand, if it does intersect more than once, like in this case, the one they drew right here, this actually hits twice, it means this is not a function with a sad face. It's really super simple. Not anything complicated with that. It's really that easy. If we want to determine if each of the following relations is a function, and then we want to state the domain and range. So I know you don't have graphing calculators at home, so I will give you a quick sketch of the graphs. So there's our axes, and the graph for y equals the absolute value of x looks something like this. Y squared equals x, the graph looks something like this. And it should go all the way down and touch there. Okay, so looking at the first one, we can draw lines all up and down across this, and there will not be a single place where that green hits our function more than one time. So we can say this is a function. And now we want to list the domain and range. So the domain here is all of the x values. So we say that this goes, if you notice, there's an arrow on the end here. So it goes from negative infinity all the way up, and there's an arrow on this end also, to positive infinity. So this is the set notation again. So the domain is from negative infinity to positive infinity. The range. If you notice, the range stops right at this line here, right down here, which is 0. So the range goes from 0, and the arrows continuously go up, so it goes from 0 to infinity. Well, infinity has to have the parenthesis around it, and this is where that set notation comes in. 0 is included, so we want to make that a hard bracket that shows that that number is included. Looking at number 2, we can draw a line right through here that hits the function twice. So this is not a function. But we still want to list the domain and range. So the domain in this case goes from the center line right here, which is 0, and the arrows tell us that it keeps going on forever. So from 0 to infinity. Again, we have that parenthesis around the infinity, and 0 is included, so it's a hard bracket. The range. This is a little tougher to see, but if you extend out a parabola, it continues going down, 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 down forever this way, and it continues going up, 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 up forever this way. So our range, in this case, actually goes from negative infinity up to positive infinity, with parentheses around both of them. Final example here, number 3. Well, right away you should be able to tell that we can draw a line, we can draw several lines in here, that will hit more than once. So this is not a function. We still do need the domain though, which is all of the x values. So where does this function go from And where does it go to on that x-axis? Well, it goes all the way over to here at -3, and then it goes all the way across to +3. And you'll notice that both of those are included, so we want to make hard brackets on both sides to show that they're included. The range is very similar to that. You'll notice that it goes from -2 down here up to +2 right here. So from -2 to +2, and they're again both included, so we want those hard brackets around it. Last thing we're going to talk about very briefly is restricted domain. If there is no domain specified, we assume the domain is the set of what we call all real numbers. And there's two ways you can denote that. The first way is you can make this fancy sign like this that stands for real numbers. Or the other way is to use our set notation, everything from -infinity to positive infinity. If y equals 2x, since 2x is always defined, the domain is all real numbers. So you can write this, or you can write -infinity to positive infinity. Both of those are okay. Now, when you get into a little more complicated things like y equals the square root of x, since a square root is undefined, when the number under the radical is negative, the domain is what we call restricted. And I know it's a small line. I'm sorry, write it underneath if you have to. So for this one, you would set what's under the radical equal to 0 and solve it. Okay, so that's for square roots. They have to be positive underneath there. And we know that a fraction is undefined when the denominator equals 0. So we're going to do 3 examples here. We're going to be good to go. And you're going to have a great night. So looking at example 1, find the domain for each function. Well, we know that we can't have a negative under that radical sign. So we're very simply going to take what's under the radical sign, 16 minus x squared, and we're going to set that equal to 0. This is the difference of two perfect squares. So we'll have 4 plus x and 4 minus x equals 0. You can t-bar that, and you'll end up with x equals 4 and x equals -4. So our domain for this is going to be the set of reals. I lied. That's not what it's going to be. The domain for this is going to be -4 is less than x, less than or equal to x, is less than or equal to +4. That will keep what's under here positive so that we don't have to worry about getting negative radicals under there, because nobody likes dealing with i's if they don't have to. Number 2 down here, we're going to take that denominator and figure out when it's undefined. So we're going to take x minus 6 and we're going to set it equal to 0. You'd add 6 to both sides and you would get x equals 6. So for this, our domain is going to be the set of reals such that x does not equal 6. I know that got a little more complicated there. The other way you could write it would be from -infinity to 6, not included, and then from 6 to +infinity. That's a little bit longer. But if you want to write it with set notation, feel free. The final example here, we want to take this denominator and set it equal to 0. So we're going to have the square root of x minus 2 equals 0. Solving radical equations, we want to go ahead and square both sides. so that our square and our square root cancels out. Didn't think you'd be using that stuff as quickly as you are now, huh? And you have x minus 2 equals 0 squared is 0. Go ahead and finish solving that. And we're going to have x equals 2. So our domain is going to be all reals such that x is greater than 2. Because any number greater than 2 will make sure that you have a positive on the bottom there. Finding the domain is a little tricky. We're going to do some practice with it in class, so don't fear. Have a wonderful evening, and I will see you in class tomorrow.